Okay, good morning everyone. So, the last class, where did we end? We were talking about confidence, we were starting to do confidence. Remember we learnt about central limit theorem. So, that gives us the shape and distribution of sampling statistic x bar, okay. And of course, we can learn about sampling distribution of S squared, which is the sample variance, and we can keep doing it, okay. But as I said, the two key parameters which you will be interested in is mean and variance. And why so? Why mean and variance alone? Because again, how is normal distribution characterized? Two parameters, mean and variance, and normal distribution is very popular because of central limit theorem. So, most often for our practical purposes, especially when we do hypothesis testing etc., we stay with mean and variance most often, okay. When we do advanced signal processing etc., we will not stay with this, but the basic confidence limits, hypothesis testing, we will be only looking at mean and variance. Throughout we will only focus on mean and variance in this course. So, coming back, so once we have determined the shape and the sampling distribution of x bar, the next question is, how do I now give limits for mean mu, okay. So, we are interested in giving limits for mean mu. So, what do I mean by that? So, I know mean is a constant, true mean, expectation of x, okay, is a constant. Now, I want to estimate this mean using what? X bar. Will x bar equal to mean mu if you compute from some small samples? No, right. So, let us assume this is my x bar. I do not have a different color, otherwise. Let us take this as okay. Okay, how do I? Let us take this as mean mu, okay. Now, what do I want to? I want to estimate this mean mu, and I know that I cannot estimate it 100% right, okay. So, I am going to give, okay, I am going to give bounds on what, x bar or mu? Bounds on mu or x bar? Huh? Bounds on x bar or mu? Mu is a constant. What do you mean by bounds? Okay. The values, the upper and lower limits are for what? This is my, so let us say I have x bar minus plus something, okay. So, what am I going to do? I am going to bound the mu, okay, mu is a constant, okay, bound, I am going to say that mu lies between this bounds, and the bounds are determined by x bar, that is the way to put it. So, I am going to say I know mu, okay, I do not know mu, but I am sure that mu will lie between these bounds, okay, and the bounds are determined by what? X bar, right. So, I understand the question, understand the concept, right. So, you have a mu and you want to find out the range or find out the range of x bar such that mu lies within this range maximum number of times or maximum percentage of times, okay. So, that is what is confidence interval is. So, if I have to write this way, I can say mu is lies between and can I be 100% sure that it will always lie within these bounds? Again, that is not possible. Why? Remember, expectation of x bar equals to mu, and the moment when we talk about expectations and probabilities, n has to be infinity. So, you say this is only true for some confidence, some percentage, okay. Some let us say 95% or 99% etc. Okay. So, we are saying mu lies within these bounds 99% of the times or 95% of the times, mu will be within these bounds. Why not 100? Again the definition of probability itself invokes limit n tends to infinity. So, whatever you do, whatever analysis you do, there is going to be uncertainty. You cannot be 100% sure that mu will lie between these two bounds, okay. There is always an element of uncertainty, okay, and therefore, you only talk about mu lying between these ranges, between these bounds some x percentage or y percentage of the times, okay. And these bounds are nothing but what? Confidence limits. These bounds are nothing but your confidence limits or confidence, the interval is nothing but your confidence interval. This interval is nothing but your confidence interval, and 95 or 99 is your confidence score. How much percentage you are confident is nothing but your confidence score. Make sense? Clear? What do I mean by that? What are we trying to do? We want to say that the mu lies within these limits some x percentage of the times, okay. We cannot say 100%, okay. So, whatever you do, there will be always outliers because of the very definition of probability, because probability is not going to be 1 unless you have n tends to infinity. Only expectation of x bar equals to mu 1 when n tends to, or variance of x bar equals to 0 only when n tends to infinity. So, for very large n still there is variance, and remember when I talk about variance, variance itself is a variance of x bar itself is what? Is a random quantity, okay. And therefore, you can never know the exact bounds also. See what, how much we are far away from the truth. We cannot know the truth, okay. We cannot also estimate the truth exactly, and we cannot also estimate the truth within the bounds 100%, okay. That is to be understood, okay. We cannot know the truth, okay. Truth is not known for a population, and we cannot estimate the truth 100% unless you do n tends to infinity, which is not possible, and we cannot even bound the estimate the truth value within a bound with 100% certainty, okay. You can keep increasing your certainty levels, okay, making it 99%, 99 point percentage, you can bound it tighter and tighter, but you can never make it to 100%. You can make it bound tighter, or you can make the bound very loose and say I can be 99% confidence. What is the what is the probability that now it will rain? Very less. So, I can say the temperature now will be anywhere between -10 to +100. I can be very sure, but will it be 100%? Because that small element of uncertainty do exist. So, that is what, and if I want to tighten the bounds, so here is an interesting, if you want to tighten the bounds, then what you should do? I know this is an easier statement to make, like the temperature now will be anywhere between -10 to 100 is a very easy statement. Now, suppose if I want to say my temperature will be for next 1 hour will be between 24 to 26 in this room or outside 25 to 27, that is a very difficult bound, right. So, the looser the bounds, your confidence will go high or go low, go high, but is that of interest to us, right? You want closer tighter bounds for mu, but with higher confidence. That is the key idea. You want tighter bounds for mu, but with higher confidence. That is the difficult part. Okay, so if you take a journal like Nature, if you go through, they will do multiple multiple hundred experiments, or if not thousands. The data availability will be very large and it will be conducted across demographics. Why? Have you ever wondered the difference between publishing in Nature and publishing in elsewhere, or clinical trials versus somebody just coming up with a drug? The reason is simple, you want tighter and tighter bounds. So, how do I get tighter bounds? How do I make the bounds tighter, but at the same time confidence higher, not lower confidence? So, what is this x bar plus or minus? What is the entity you will want to add here? What is the variance of x bar? So, standard deviation is, so what is natural to add here, x bar plus or minus? Sigma by root n, make sense? Now, is it always, am I interested in 1 sigma? Am I always interested in 1 sigma? Not necessarily, right? I may want what? 95% confidence. I may want what? 99% confidence, right? And remember, your normal distribution is, how is it distributed? Suppose I want 95%, my data should lie the mean should be within, I should be 95% confident that the mean lies within the bounds. Let us ask this question. I want to be sure that my mu lies within the bounds 95%. Now, you also understand why 100% is not possible, then you are covering the entire normal distribution. Why are we talking about normal distribution now all of a sudden? How did this, for bounds I am using normal distribution, where this normal distribution came from? That is because of central limit theorem. Okay. Now, I know x bar follows Gaussian. Under the assumption of central limit theorem, x bar follows Gaussian distribution, and therefore, the x bar's distribution is Gaussian. So, I am going to bound mu using x bar, which is normally distributed. Now, in x bar, now if I say my mu has to lie within the bounds 95% of the time, where are the bounds to be placed on? It is going to be on the normal distribution, right. So, now you know that normal distribution is what? Symmetric. So, let us say alpha is 0.05. What do I mean by that? Alpha 0.05 means what? The area, left out area is what? 0.95, right? 0.95, 0.05 is 1, right? So, left out area is what? 0.95. So, my alpha equals to 0.05 is what? I am only uncertain 5%, right. If alpha equals to 0.2, I am defining a number called, defining an entity, we will make it explicit. I am defining an entity called, quantity called alpha, which is measure of the error that I will make, or which is a measure of that mu can lie above or below this bounds. That is, I want the mu, I want only 5% of the times the mu to be above or below this bounds. So, I say alpha is 0.05, okay. And what is this value? This will be alpha by 2, this will be alpha by 2 by the way of symmetry, okay. Now, if I want 95% now, what should be here? Is that alpha? This is not 1 sigma, right. This is the value of CDF corresponding to, so let me write this. What is Z alpha by 2? Value of CDF corresponding to alpha by 2. What am I saying? That is this region, and this is this region. This point is Z alpha by 2. This is Z alpha by 2. So, mu lies between what? X bar minus Z alpha by 2 and X bar plus Z alpha by 2. So, that way I can be saying 95% of the time mu lies within this region. What is the alpha I have chosen? 0.05. If I choose alpha as 0.05, I can be sure that mu lies 95% of the time within these bounds. Does it make sense? Right? Mu lies within these bounds 95% of the times, because I have chosen alpha to be 0.05, which is the 5% that mu will lie outside the bounds. Okay. And Z alpha by 2 is nothing but the value corresponding to. So, let me show you the normal table, then you will probably get this as well. Okay, let us look at this. Can somebody tell me where it is Z alpha by 2? How do I see this? Z alpha by 2. The CDF value corresponding to Z alpha by 2, which is alpha is 0.05, means alpha by 2 is 0.025. How do you see the area? Z corresponding to 0.025, that is what it is, right. Z corresponding to 0.025. 0.025. Okay. So, this is going to be 1.96. Z corresponding to 0.025. Z alpha by 2 is the area, the value of Z corresponding to 0.025. What is this? 1.96. You are not given Z, you are given alpha. You want to find out the corresponding Z, it is inverse. Okay. So, the Z value corresponding to 0.025 is what? 1.96. It is expected, because within 1 sigma how much percentage you have? 67% something. Within 2 sigma you have 90, more than 95. So, you are in between, right. So, if you look at this, 95% corresponds to plus or minus roughly. So, you are having 1.96, close to 2 sigma, that is what it is, right. Make sense? Okay. So, if I want 99%, how will I do? I want to be 99% accurate. What is the Z alpha by 2 value? 99% accurate. Look at the table. I want to be 99% accurate, for 99% sure that the X bar value lies within the bounds, mu lies within the bounds. 0.05 by 2, 0.01 by 2, which is 0.005. Look at 0.005, should be between these two, 2.57 or 2.58. Make sense? 0.0051 to 49. I do not have 50 exactly, 51 or 49. This corresponds to 2.57 or 58. Right? You able to look at this 2.57 you go down 0.0051, 0.0049. So, I have 2.57 or 2.58 is the answer, which is expected. If I want to be very sure, will the Z alpha by 2 increase or decrease? Naturally, your bounds will increase, right, because you want to be more sure, then naturally your bounds will increase. How do I tighten the bound? So, Z alpha by 2 is fixed now. Z alpha by 2 is what? 1.96 for 95 percentage and 2.58 for 99 percentage. So, only the bounds is going to increase. So, what do I do now? How do I tighten the bounds? So, how do I bound it? How do I reduce the bounds? You understand? I want to be 99 percentage sure, not 95, 99. That means Z alpha by 2 is higher. Okay. X bar is something. Okay. X bar is now a constant. X bar mu is a constant. X bar is on the both the sides. Now, how do I tighten the bounds? How do I tighten the bound? What is the only parameter that you have leverage? You have that you can tighten the bounds. Look at this equation. Z alpha by 2 is fixed, no. If I want to be more and more sure that Z alpha by 2 is going to increase. So, if I want 99.9 percentage of the data to be lying within the bounds, 99.9 percentage of the time mu lie within the bounds, then means Z alpha by 2 will become 3 sigma, it will be more. It is not going to reduce at all. As you want more and more confidence, Z alpha by 2 will only increase. So, now what is the only thing parameter which you have to tighten the bounds? Huh? Huh? X bar is from the data. What can I say? Can you fetch the data? N. So, if I keep increasing n, then these bounds can reduce. And the other one is sigma. Sigma is again not in your hand. But in biomedical, especially in clinical trials, etc., will sigma be large or small? Sigma will be small. Should be small is what we want, desire. Desire is not the reality. We want desire sigma to be 0, which is very good. But what will be this sigma in biomedical or clinical trials? You go to the doctor, okay. Let us say a female goes to a doctor, I go to the doctor, right. The way the mental model the doctor builds, will it be same for both of us? Right. Some 20-year goes, 40-year goes, 60-year goes. What is it? So, 20-year goes, let us say 20-year you go, you have a fungal infection in their leg, and 10-year, let us say 10-year goes, he has a fungal infection in the legs. What will they do? A doctor? Very common fungal infection. What do they do? What is the question they will ask? 10-year-old. Just simple fungal infection in the leg, 10-year-old, what will they ask? Did you go to beach, play in the sand? Your hands, is it only in the legs or what is in the hands? Did you walk barefoot? Okay. 40-year-old goes to the doctor with a fungal infection in the leg. What will they ask? In fact, this happened to my friend. Then I realized, then I got, I actually started taking care of myself better. So, what 40-year-old goes with a fungal infection? What do they suspect? No idea. Biomedical engineers.
They might ask for any kind of internal disease.
Go take blood test, blood sugar test. Diabetes. It turned out for my friend, it is simple, diabetes. 40-year-old, he goes with a fungal infection, she says, the doctor says, okay, go have a blood sugar test, we will get your diabetes tablets ready. She was very sure, went, came back, yes, nothing to suspect more than that, right. So, what is the variability in you know, in the age group, with the gender is so large. Okay. So, sigma is not in our control, and typically for biomedical experiments, biomedical cases, sigma is higher. Now you understand. So, if you take some of the journals in biomedical field, like biomedical and medicine, especially like New England Journal of Medicine, its impact factor is 170 plus, something big number, very big, which is unheard of in other domains. Reason, to prove one thing very strong, even a small hypothesis, okay, even a smaller hypothesis, but you have to be very confident, you need to conduct huge amount of experiments, okay, and you have to be systematic in considering all the factors. Okay. This is Richard Feynman, you all know Richard Feynman, physics guy, right. So, he was saying, you know, today we conduct, you know, in his days even he was saying he was not happy about the experiments, because in you know, if you want a simple hypothesis like, you know, a mouse could use smell as a source, or you know, it uses smell or intuition, what are the sensory, or you know, what are the you know, what I call short of word, like you know, sensory organs and other aids that a mouse uses to figure out the cheese, is the question. Simple, it appears simple, right, it has its own value. Now, what kind of experiments one can do? Simply one can say, close the nose or something, have cheese, see if it tracks. Okay. Now, this, for this simple hypothesis, it appears simple although not simple. Okay. Researchers have done 2 years of experiments. Why? Because they have to make sure the mouse does not remember the path, set it in a maze, okay. Systematically consider factors, climatic conditions, systematically consider factors and then eliminate them, right. So, when you start looking at bio experiments, especially you know, when you play with, start with human organs or human cognitive, the experiments are going to be time taking, you have to consider various factors, sigma is not in your hand, the variability will be usually higher. So, the only leverage you have is n, okay, clear. So, this is what the confidence interval is, x bar. So, shortly mu is what I have, okay. So, a point estimator of a population parameter is a, this is what we learned, we are talking about large sample confidence interval. What do I mean by why large sample? Where did I use this assumption of large sample? Gaussian distribution, otherwise I do not know the distribution of x bar, okay. For a large sample the distribution is x bar, okay. And what do I have? Mu equals to plus or minus x bar plus or minus z alpha by 2 into sigma over root n, with how much percentage confidence? With how much percentage confidence? 95, I wrote z alpha by 2, I did not write 1.96. What is the general percentage of confidence? 1 minus alpha percentage confidence, okay. So, this is the generic scheme, okay. So, mu equals to x bar plus or minus z alpha by 2 into sigma by root n with a confidence of 1 minus alpha percentage. So, what is the error? What is the error? What kind of error is it? What is the error here? What is the error meaning? What kind of error? What kind of error are we talking about? We cannot talk about now error unless we have an hypothesis, but what is this alpha? Alpha is the uncertainty that the mu will lie beyond these bounds. So, alpha is the uncertainty level, that mu lies beyond this bounds, clear. Okay, so this is for large sample, in other words this is, and remember sigma by root n is nothing but comes from sigma of x bar. So, we are still talking about 1 sigma 2 sigma only, okay, nothing but sigma over root n because it is sigma of x bar, sigma of x bar is nothing but sigma over root n. This is all we talked about 1 minus alpha, alpha is the uncertainty about mean mu. Okay. Now, in reality we will not know sigma, right, you will not get to know sigma in reality. So, what do we replace sigma with? We do not have a choice, we replace with sample variance or sample standard deviation, we do not have a choice. So, sigma becomes yes. So, this is what I have. Okay. So, for large sample, for the confidence interval to be valid, the sample must be random IID. Okay. So, that I cannot ensure that, at least I will ensure that the sample is taken randomly, so that there are no dependencies in the sample taken, and the sample size n must be large. Now, we will slowly get into small sample. Okay. We have seen so far large sample. Okay. Now, what happens if the sample size is less than 30? Pretty much possible. If I ask you to do 1000 experiments, conduct 1000 experiments or even 40 experiments, in a clinical trials, small trials, going to the hospital, getting that much data is not an easy task, right. If you want to do experiments of a rare disease or even a normal like Parkinson's or Alzheimer's, finding out 40 participants with same level, that is the challenge. You can find 40 Parkinson's people, but are they at the same levels? Confounding will be there. If you do not do experiments at the same level, you will not know, right. A drug may be effective at an initial stage, at a later stage the drug may not be effective. So, you may want to do it at a different levels. So, it is not going to be easy that always you will find large number of participants or large number of data. Okay. So, n can be small, and usually in what? In biomedical experiments n will be smaller. Okay. So, now the assumption of Gaussianity does not hold, x bar is not going to follow Gaussian distribution. Okay. X bar is not going to follow Gaussian distribution, that is where the problem is. So, sampling distribution of x bar is unknown. Okay. Then what do I, how do I go doing it? Okay. The sampling distribution of x bar is known. Okay. So, how do I start doing this? Then there is an assumption that we make, that is a very important assumption. With this I will stop for today. There is an important assumption which we make. So, in case of small samples, if the underlying population is normal, if the underlying population is normally distributed, what is the assumption I am making? I am making assumption about the underlying population itself. Okay. Earlier in x bar I had no assumption about the underlying population except that it is independent, that means the samples are taken at random, whereas here I am going to make a very important assumption. I am making an assumption that the underlying population itself is normal. If the underlying population is normal and if the sample size is small, then mu is, the bounds on mu is mu equals to x bar plus or minus T alpha by 2 into S by root n. What is T alpha by 2? Like Z, T is a distribution called student's T distribution. Okay. If the population is normal and if the population is underlying population is normal, then I can show that x bar follows T distribution instead of normal distribution. Okay. If the sample size is small, that is less than 30, and if the underlying population is normal, then I can show that x bar follows t distribution. If the population size is large and IID, then what can I show? X bar follows normal, which is what central limit theorem is. It is very popular because it does not make any assumption about the underlying distribution except a limiting case of independency, whereas here it is very limiting. You have to know the underlying population and it should be normal. If the underlying distribution is not normal, this will not work. Okay. So, typically small samples you will have a headache. Dealing with small samples you will have a problem. Okay. There are various methods to work around it, and if time permits we will learn about what is called as bootstrapping methods, okay, to take care of this kind of issues in the small samples. But when you deal with small samples, the typical issue is what is the distribution of x bar. It is only true when the underlying population is normal, but how do I ensure that the underlying population is normal? I do not know. Okay. That is a catch. Okay. If the underlying population is normal for when n is small, then you have the bounds on mu to be mu equals to x bar plus or minus t alpha by 2 into sigma over root n. In other words, the t and x bar will have similar distributions. T will be slightly lower compared to normal at the peak values. Okay. So, t distribution and normal distribution will merge when n becomes greater than 30, and that is the reason why n I keep repeating 30, because after 30 the t distribution becomes normal distribution. Okay. For small sample n is less than 30, then you choose t distribution, otherwise t becomes normal. But for t the important assumption is the underlying distribution is normal, whereas for a central limit theorem the underlying distribution need not be normal or anything, it just need to be IID. Okay. That is why central limit theorem is very popular compared to this kind of one. Okay. This is for small sample. Okay. So, we have given confidence interval for large sample as well as small samples. Okay. For a confidence interval to be valid for a small sample, the sample must be random, of course, independency is obeyed, and the population must have a relative frequency distribution that is approximately normal. Okay. Those are the conditions. Okay. I have given some examples that we can take about it. So, the next class we will talk about confidence intervals for proportions, and then we will move on to determining the sample size. How do we do it? Determining the sample size, etc. Okay.